Hello, this is John Miyares, and in this lesson, we are going to talk about hyperbolas. Now, hyperbolas tend to be much more intimidating than ellipses, but a lot of the work we're going to do with them is going to be very similar to what we did with ellipses. There are a few different properties that hyperbolas have that ellipses do not, so we'll be talking about them here. But at the end of the day, we're still going to be generally looking at two types of problems. Those where you're given the equation and have to find the properties and sketch the graph, and others where you're given the properties of the graph and have to determine the equation. Also, just like with ellipses, the textbook separates these into two sections, those centered at the origin in section 11.3 and those centered elsewhere in section 11.4. We're going to focus in this lesson about those centered somewhere that's not the origin, and by doing that, it should make our study of those that are centered at the origin that much easier. I hope. Now, as a reminder, if a question comes up during this presentation that isn't answered by the recording, be sure to write it down, then you can send it to me as an email, or better yet, you can post it on the discussion board under the general questions and items to share forum. With that, let's get started. So, what is a hyperbola? The formal definition says a hyperbola is the set of all points in a plane for which the absolute value of the difference of the distances from the two fixed points, or foci, is a constant. The midpoint between the foci will be the center of the hyperbola. Now, unlike ellipses, it's very hard to look at how we're supposed to draw these out freehand because it's not like we can easily just put push pins in a string to draw it out. But you should be able to see what's going on in this diagram. Just like ellipses, we're going to have these values A and B, which will represent the horizontal and vertical radius. And also we have C, which is the distance from the center point to the focal points. The dashed gray lines running diagonally through this graph are asymptotes. And just like asymptotes you may have worked with in previous courses, these asymptotes act as boundary lines that the graph of the hyperbola will approach but never touch or cross. The focal points, or the foci, this time are further from the center than we saw with ellipses, but in a similar way, the curves of the hyperbola are still bent around the focal points. There are two types of hyperbolas we're going to be working with in this unit. One will open left-right, while another will open up and down. In these diagrams, you see them both on display. The equations for the two are slightly different from each other, but the processes and procedures we will use to find their properties are very similar. The first hyperbola opens left-right, and its equation is given here as x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1. Now, as you look at this, the equation looks very similar to an ellipse, except in between the two main terms, we have a minus sign instead of a plus sign. So if they look that similar, they must have similar features, right? Well, yes, the center point will still be at the point HK, just like we've already seen with circles and ellipses. We can still mark the horizontal radius as A and the vertical radius as B. Since this opens left-right, the vertices of the hyperbola will be at H plus or minus A, comma, K, and are labeled here in the sketch. Now a couple of new terms. We don't have a major axis and a minor axis like we did with ellipses. With hyperbolas, what we might think of as the major axis, the one that goes through the vertices, is called the transverse axis, and that's the horizontal dashed line that goes through the vertices, the foci, and the center. The vertical axis of symmetry that runs through the center is called the conjugate axis. But I'll just say right now that our textbook doesn't really talk about it being called that at all. Now, hyperbolas have two asymptotes. The slopes will be based on our vertical and horizontal radii A and B. Given, and when they're given there, plus or minus B is going to be the rise, and A is going to be the run. So the asymptotes also will pass through the center point HK. For those of you familiar with the point-slope form of a linear equation, we're going to see that demonstrated here, where you have normally y minus y1 equals m times x minus x1. Here we have y minus k equals plus or minus b over a times x minus h. The focal points will always be on the transverse axis, which in this case is horizontal. We'll measure them as c units to the left and right of center. The equation to generate the distance c, however, is going to look more like the Pythagorean theorem, with a squared plus b squared equaling c squared. Finally, so that we don't forget it, the key factor in this equation that will make it open left-right as opposed to up and down will be that the x squared term in the equation is positive and the y squared term is negative. While we'll get into this a little bit later in the presentation, if the order of the subtraction is reversed, that is, if it were the y squared term minus the x squared term, then the hyperbola would open up down. And of course, if there was a plus sign in between the terms, then we would have an ellipse. Before we move on to the first example, I'm going to pause here for a few seconds so you can process all the information that's on this slide. Here's our first example. Sketch the graph of the given equation. Identify the vertices, the foci, and the equations of the asymptotes. Our equation is given in standard form as x plus 3 quantity squared over 16 minus y minus 2 quantity squared over 9 equals 1. So how are we going to sketch this parabola? Here's my suggestion. Think about the processes you would use to sketch this if it were an ellipse instead of a hyperbola. Most of the properties are the same, so let's start with that. The horizontal radius will be the square root of the denominator of the x term, which will be the square root of 16, or 4. The vertical radius will be the denominator of the y term, which will be the square root of 9, or 3. Since the equation is showing as x squared minus y squared, the transverse axis will be horizontal and the hyperbola will open left to right. So now let's start thinking about how we're going to sketch our graph. The center is going to be at the point HK, which, just like with ellipses, we can read off of the values of what's being subtracted from x and what's being subtracted from y. Here, the coordinates of the center will be -3, 2. So we can plot that here. The vertices will be 4 units to the left and 4 units to the right of center, which places them at the points -7, 2 and 1, 2, which we can plot here. Now, if we were graphing an ellipse, our next step would be to find the co-vertices. And you might be asking yourself, why do we care about those here? Well, it'll be obvious in a second. The co-vertices are going to be 3 units above or below the center point, which will place them at -3, 5 and -3, -1, as shown here. Now, if we were sketching an ellipse, we would want to draw our sketch through those 4 points. Instead, we're going to put a rectangle or a box in place of where we would have put that ellipse uh, if that was what we were drawing. So here, where I've drawn an ellipse, we want to put a rectangle in instead. Now, let me just move that ellipse out of the way. Why is this rectangle important? Well, for a few reasons. First, we're going to construct asymptotes through the opposite corners of this box. Based on how this box is constructed, the slopes of the asymptotes will be b over a and negative b over a and intersect each other at the center point. So the box is going to serve as our guidelines for constructing our asymptotes. Second, we know where the vertices are located, and we know that the hyperbola opens to the left and right. So we can draw our hyperbola with the given vertices and have them open and approach those asymptotes as they open up, like so. Now that we have our sketch in place, we can identify all the key properties of the hyperbola. The vertices, as discussed before, will be at the points -7, 2 and 1, 2. To find the foci, we must compute a value for c. As we showed back on slide 4, the formula to compute c in a hyperbola is c squared equals a squared plus b squared, which for this problem will be 16 plus 9, which equals 25. Then we take the square root of that to get c equals 5. Just like with ellipses, the focal points will be c units from the center of the hyperbola. And since it opens left-right, we're going to add and subtract 5 units from the x-coordinate of our center to locate the foci. Here, we can see that they will be at the points -8, 2 and 2, 2, which I can graph here. The equations of the asymptotes can be found by applying the point slope form of the equation of a line, knowing that the slopes will be plus or minus b over a and the vertical radius over the horizontal radius as they pass through the center point hk. Given that the center is at -3, 2, the vertical radius is 3, the horizontal radius is 4, then the equations for the asymptotes will be y minus 2 equals plus or minus 3/4 times the quantity x plus 3. Now again, I'm going to pause here for a bit so you can process everything that you see. Now, the second type of hyperbola is one that opens up down, and its equation is given here as y minus k quantity squared over b squared minus x minus h quantity squared over a squared equals 1. As you can see, the main difference is in the order of the subtraction, but otherwise, many of the properties are going to be the same. The center point will still be at hk. We can still mark the horizontal radius as a and the vertical radius as b. But with these, we have to pay very close attention to which is which because we're used to seeing uh, a come before b when writing down these equations. What I want to remind you of is when we looked at ellipses, a comes before b just as x comes before y in the alphabet. But a is always associated with x because both of those are associated with horizontal components of the graph. B always goes with Y because those are tied to vertical components. Just be careful that you don't mix these up. If you just remember that A goes with X and X is horizontal, B goes with Y and Y is vertical, then you should be okay. Since this hyperbola opens up and down, the vertices will be at h, comma, k plus or minus b. The transverse axis is going to be vertical, and the conjugate axis is going to be horizontal. The equations of the asymptotes are going to be the same regardless if your hyperbola opens left right or up down. So they are going to be y minus k equals plus or minus b over a times x minus h. Also, the focal points will still be on the transverse axis, which in this case is vertical, and we will measure them as c units above and below the center. The equation to generate the c value will be the same as it was for a hyperbola opening left-right. C squared equals a squared plus b squared. Finally, so that we don't forget it, the key factor in this equation that will make it open up-down as opposed to left-right will be that the y squared term in the equation is positive and the x squared term is negative. Again, I'll pause here for a few seconds for you to process all the information on this slide. Here's example 2. Just like before, we want to sketch the graph of the given equation. Identify the vertices, the foci, and the equations of the asymptotes. Our equation is given in standard form as y plus 4 quantity squared over 25 minus x plus 1 quantity squared over 16 equals 1. To sketch this hyperbola, we're going to do the same thing we did when we were approaching ellipses. So let's start with an empty graph. The horizontal radius will be the square root of the denominator of the x term, which will be the square root of 16, or 4. The vertical radius will be the square root of the denominator of the y term, which will be the square root of 25, which is 5. Since the equation is showing y squared minus x squared, the transverse axis will be vertical and the hyperbola will open up down. So now let's start thinking about sketching our graph. The center is at hk, which will be the point -1, -4. Don't forget that with the way the equation is written, the y's come in front of the x's, so it's easy to mix them up and get this backwards. Be mindful that the x coordinate of the center is always being subtracted from the x, and the y coordinate of the center is always being subtracted from the y. It is very easy to make this mistake, but if you're using a program like Desmos to help you generate your graphs, it's a very easy mistake to catch when it's made. So now we have our center point plotted here. Next, we have to plot the vertices, which are going to be 5 units above and below the center point, because, of course, the hyperbola is opening up, down. That places the vertices at the points -1, 1, and -1, -9. The covertices, which we'll need to plot in order to sketch our box and draw in our asymptotes, are going to be 4 units to the left and to the right of the center point because our A value, the horizontal radius, is 4. That's going to place these points at 3, -4 and -5, -4, as shown here. Now again, if I were drawing an ellipse, we would want to draw our sketch through these 4 points. But instead, we're going to be putting a box in here in its place, in the place of the ellipse that we would have been drawing. So again, where in section 11.2 I would have drawn an ellipse here, we're going to put a rectangle instead. With this box in place, we can construct asymptotes through the opposite corners of this box. And based on how the box is constructed, the slopes of the asymptotes will be b over a and -b over a, and intersect each other at the center point. Next, once the asymptotes are in place and we know which are our vertices, we can draw the hyperbola. Since we know it opens up and down, we can sketch our graph with the vertices at the top center and bottom center of the box, and then we can expand the curves outward towards the asymptotes, being careful not to touch them or cross them. Now that we have our sketch, it's a lot easier to answer our questions. The vertices will be at the points -1, -1, and -1, 9, as discussed before. To find the foci, we must compute a value for c. The formula is given as c squared equals a squared plus b squared, which will be 16 plus 25, which equals 41. So c equals a square root of 41. Since this opens up down, the foci will be square root of 41 units above and below the center point. Unfortunately, those aren't going to have particularly clean values here. For the asymptotes, we're going to use the same equation as we did in example 1, where the slopes are going to be plus or minus b over a, and they're going to pass through the center point hk. This is going to simplify as y plus 4 equals plus or minus 5/4 times the quantity x plus 1. Now again, I'm going to pause the video here for a bit so that you can process everything that you see. All right, now that you've seen the basics, it's time to look at some harder examples. And just like we had with circles and ellipses, you're not always going to have your equation in standard form first. You're going to have some cases where you're going to have to complete the square first. So just like we did with ellipses, we're going to complete the square for x and y. And just like before, we'll need to regroup the terms so that the x's are with the x's and the y's are with the y's, and then we can leave some space to insert constants. So if this is our equation, x squared minus y squared minus 8x plus 2y plus 13, we're going to move those two middle terms around so it looks like x squared minus 8x plus, minus y squared plus 2y equals -13 after we move the plus 13 to the other side of the equation. Now, just like with ellipses, the coefficients of the squared terms won't necessarily all equal 1. We're going to need to factor out the lead coefficient in that case, in case we see some problems. Now, just like with ellipses, if the coefficients of the squared terms don't equal 1, we will want to factor out the lead coefficient from those terms that are going to cause problems. In this example, it isn't obvious that we have a problem since it looks like the coefficients of the squared terms are both 1. But where it's deceiving is that in front of the y squared term is a minus sign, which means that the coefficient of the y squared term is -1. So we're going to have to factor out a -1 out of the two y terms in order to get y squared minus 2y inside the parentheses. Next, we want to complete the square for both x and y. With the x terms, we're going to take half of the -8, which is -4, squared is 16. So just like before, we're going to add 16 on the left in order to complete the square for the x's. And we're going to add 16 on the right side in order to keep things balanced. Now, with the y terms, we have to be careful. When completing the square for the y's, we'll look inside the parentheses and see half of -2 is -1, squared is 1, and add 1 inside the parentheses. However, remember, everything inside the parentheses is being multiplied by a minus sign outside of the parentheses. So in order to keep the equation balanced, we don't want to add 1 to the right side, but rather we want to subtract 1 on the right-hand side. From here, we want to factor each trinomial into perfect squares, then simplify the right-hand side. So we'll get x minus 4 quantity squared minus y minus 1 squared equals negative 13 plus 16 minus 1, which equals 2. Our last step is going to be to get this equation into standard form, which requires that the equation equal 1 on the right side and not 2. So we're going to divide everything by 2 to get our final answer of x minus 4 quantity squared over 2 plus y minus 1 quantity squared over 2 equals 1. Now that the equation has been rewritten into standard form, we can start to identify all of the properties of the hyperbola. The horizontal radius will be the square root of 2, and the vertical radius will be the square root of 2. The decimal equivalent for the square root of 2 is approximately 1.414. The center will be at hk, recognizing that in this form we have x minus h and y minus k, giving the center at 4, 1. The transverse axis is horizontal because the equation is going to be in the form x squared minus y squared. So the vertices are going to be at the square root of 2 units to either side of the center horizontally, which would place them at 4 plus or minus the square root of 2, comma 1. To find the foci, we'll take the sum of the two denominators here, a squared plus b squared, which gives us 2 plus 2 equals 4. So c equals the square root of 4, which is 2. Since the transverse axis is horizontal, the foci will be 2 units to the left and right of center. That places them at the points 6, 1 and 2, 1. Finally, the asymptotes will be two straight lines that pass through the center point 4, 1 that have slopes b over a and negative b over a, as shown here. Since a and b are both equal to 2, the slope will reduce to 1 and negative 1. Finally, we can sketch the graph. I'm not going to show it all step by step, but you can see here that the hyperbola has all the key properties we're looking for. We would start just like before by marking the center point at the coordinates 4, 1. Then we would locate the vertices and the co-vertices in order to form our box. In this case, our box is a perfect square. Since the a and b values are, we draw out our asymptotes through the corners, then construct a hyperbola to open left, right from the sides of the box, opening outward towards the asymptotes, but never crossing them. The foci are marked at 6, 1 and 2, 1, which are 2 units to the left and right of center. Here's one I'd like for you to try on your own. What I'd recommend is that you pause the video long enough for you to work through all the steps, just like we did in example 1. What you should notice is that you've got a y squared term minus an x squared term, which means that this hyperbola is going to open up, down. The process is going to be very similar to what you've done before, where you'll want to rearrange the terms to put the x's and y's together, then factor out those lead coefficients so that we'll be able to complete the square more easily. Then, of course, we'll leave some space to insert constants. Complete the square for each term inside the parentheses, then add the value on the right to keep the equation balanced, keeping in mind that you'll have to multiply those constants by whatever lead coefficient is left, and you'll need to watch out for that negative sign in front of the 4x squared term. Finally, once you have the factored expression, you'll want to divide both sides by whatever constant is left on the right-hand side in order to get it all equal to 1. Then you can simplify the results. I'm going to pause here for a bit to let you get your chance to work through this one on your own. Okay, here we go. So we're looking to regroup the terms of this equation. To get the x's grouped together with the x's and the y's grouped together with the y's. So that's going to give us 9y squared plus 54y minus 4x squared plus 8x equals negative 41 after we move the 41 to the other side of the equation. Next, we factor out the lead coefficients of 9 that are going to be in front of the y squared term and the minus 4 in front of the x squared term to get what you see here. Be very careful when you factor out the negative sign with the x squared term, as the middle term is going to become negative 2x. To complete the square, we need to look inside each set of parentheses and determine the constant that will allow that expression to factor as a perfect trinomial square. For the y's, we have to take half of 6 to get 3, and 3 squared is 9. So while we can insert a 9 inside the parentheses, we need to remember that everything inside the parentheses is being multiplied by the 9 on the outside. So we don't want to add 9 to the other side. We actually want to add 81 to the right-hand side. Similarly, we want to look at the x expression, and we see that the middle term is negative 2. Half of negative 2 is negative 1, and negative 1 squared is positive 1. This means to complete the square inside the parentheses, we want to add a 1. However, everything inside the parentheses is really being multiplied by the minus 4 on the outside. So on the right-hand side, we're going to subtract 4 times 1, or just subtract 4. Now, factoring each piece and simplifying the right-hand side, we have here 9 times the quantity y plus 3 squared minus 4 times the quantity x minus 1 squared equals 36. So we're almost done, but not quite. We still need to get this expression to equal 1 on the right-hand side. So we're going to divide both sides by 36 and reduce the fractions to get y plus 3 quantity squared divided by 4 plus x minus 1 quantity squared divided by 9 equal to 1, which is our equation in standard form. Now that the equation has been written in standard form, we can identify all the properties we're supposed to. The horizontal radius will be the square root of 9, which is 3, and the vertical radius will be the square root of 4, which is 2. The center will be at hk. Recognizing in this form we have x minus h, y minus k, which gives the center at 1 comma negative 3. Being mindful that the way this is written, the y's in the equation are coming before the x's this time. Very common mistake. Keep an eye out for that. I see many people losing points on quests because they would write the center point as negative 3, 1 instead of 1, negative 3. The transverse axis this time is vertical because it's written in the form y squared minus x squared. Now you might be thinking to yourself, wait a second, the horizontal radius is bigger than the vertical radius. So shouldn't the horizontal radius be the major one, and that would make it open left, right? Well, again, that would work for an ellipse, but not a hyperbola. The shape of the hyperbola, whether it opens up, down, or left, right, is determined by the order of the subtraction of the terms. That it's y squared minus x squared or x squared minus y squared. The A and the B do not impact whether it opens left, right, or up, down. Anyway, the vertices are going to be 2 units above and below the center vertically, which would place them at 1, -1, and 1, -5. To find the foci, we'll take the sum of the squares, excuse me, we'll take the sum of the two denominators, a squared and b squared, to have 9 plus 4 to get 13. So c will be the square root of. Since the transverse axis is vertical, the foci will be the square root of 13 units above and below the center. So we will see them here at 1 comma -3 plus root 13 and 1 comma -3 minus square root of 13. Finally, the asymptotes will have slopes that are plus or minus b over a, which is plus or minus 2/3, and the asymptotes must pass through the center point 1, -3. So the equations, normally written as y minus y1 equals the slope m times x minus x1, can be written as y plus 3 equals plus or minus 2/3 times x minus 1. At this point, we can sketch the graph like we did before. I'm not going to show it all step by step. But here you will see the hyperbola with all of the key properties. The center is at 1, -3. The vertices are at 1, -1 and 1, -5, while the covertices that help us construct the box are at -2, -3, and 4, -2. Now, some of you might be asking, if they're not part of the graph, should we be calling them covertices? Well, we do need them to help us construct our box and to construct the asymptotes. So also, if the signs were reversed in this equation, the covertices of this up-down hyperbola would have been the vertices of a left-right parabola. So it doesn't hurt to label them as such. The foci here are going to be at 1, comma, -3 plus or minus the square root of 41. Now we're ready to look at examples where we want to find the equation of the hyperbola given some known properties. I've got a couple of examples to work through here. So here's the question. Find the equation of a hyperbola with vertices 0, -1 and 0, 1, and foci 0, -2 and 0, 2. So this one is going to take a bit of thought. We know there are two standard forms for the equation of a hyperbola, and one of the things we need to do is figure out which of these we need to use. Does this hyperbola open left-right, or does it open up-down? In either case, our goal is going to be to use what we know to see if we can figure out the values of h, k, a, and b will be in whatever form of the equation we're going to use. So what do we know so far? Well, we know where the vertices are. We know where the foci are. So we should be able to get to the center point, because the center point will always be the midpoint between the vertices, or the midpoint between the foci. So for this problem, the midpoint between 0, 1 and 0, -1 is the origin 0, 0. We can also see that based on their position, the vertical radius has to be 1. 0, 1 is 1 unit above the origin. 0, -1 is 1 unit below the origin. That must mean that the transverse axis is going to be vertical. Therefore, we know we're going to end up having to use the second form of the equation that has the y squared minus the x squared factors shown here. Since we know the center is at 0, 0, we can plug in 0 and 0 in for h and k as shown above. Next, since we know that the b value, the vertical radius, is 1, we can also plug that into the equation as well. So we have y minus 0 squared over 1 squared minus x minus 0 squared over a squared equals 1. Now, the other information we're given is about the foci. Since the foci are at 0, -2, and 0, 2, then the c value, the distance from the center to the focal points, must equal 2. So we know the value of b equals 1. We know the value of c equals 2. We can solve for the value of a by using the formula c squared equals a squared plus b squared. Or in this case, we see 2 squared equals a squared plus 1 squared. And squaring this out, we get 4 equals a squared plus 1, which can be solved as a squared equals 3. Substituting that in here, we end up with a final answer of y squared over 1 minus x squared over 3 equals 1. This last example is a little bit different and may require a little bit more thought. Here, we want to find the equation of a hyperbola with asymptotes at y equals plus or minus 3/4 x, and one of the vertices is at the point 0, 3. Our goal is the same as it was before, in that once we know which version of the equation we're going to use, we are going to have to solve for h, k, a, and b in this hyperbola. So, what do we know? Well, the asymptotes of a hyperbola always cross each other at the center of the hyperbola. The equations of the asymptotes would be y equals 3/4 x and y equals negative 3/4 x. Both of these asymptotes have y-intercepts of 0, which then suggests that they must cross each other at the origin 0, 0, which means that the center of a hyperbola is going to be 0, 0. Next, we're told that there's a vertex at 0, 3. This vertex is vertically above 0, 0. So this tells us that the hyperbola must open up and down, and that the vertical radius, b, must equal 3. Now, if it opens up down, we're going to use the second form of the equation again that's shown above. Y minus k quantity squared over b squared minus x minus h quantity squared over a squared equals 1. Since we know the center is at 0, 0, we can plug in h equals 0 and k equals 0. We also know that b equals 3, so we will have 3 squared as the denominator of the y term. And we show that here. So what else do we know? Well, the slopes of the asymptotes are plus or minus b over a. If b is 3, and the slopes of the asymptotes are going to be 3/4, that must mean that the value of a is 4. This is going to allow us to substitute a equals 4 into our equation and simplify things pretty quickly to get y squared over 9 minus x squared over 16 equal to 1. Now, something that I want to point out here real quick. If we had the vertex at the point 0, 6 instead of the point 0, 3, but still had to find an a value, knowing that the slope of the asymptote is 3/4, then we could use proportions or equivalent fractions to figure out what the value of a should be. If b were 6 and the slope was 3/4, in that case, then the value of a would be 8, since 6 over 8 would reduce to 3 over 4. I didn't put that example here, but you may see something like it on a problem challenge or on a homework assignment in WebAssign. So that does it for another lecture video. You should be okay now getting started on the problem challenges for 11.3 and 11.4b. As a reminder, the biggest difference between the two sections is that all of the hyperbola problems from section 11.3 have their center at the origin 0, 0, while the hyperbolas in section 11.4 have their centers at some point other than the origin. The processes and procedures are going to be pretty much the same. So here are the problem challenge problems for the two sections that we're covering. Some of you might be wondering why we're doubling up like this and having so many problems to start with when I said on the first day that problem challenge problems would only involve 5, maybe 6 problems at most, and here for the last couple nights we've seen 10. Well, that just happens to be the nature of this particular unit. As we progress through future units, there may only be one problem challenge to work with in a given night that will be 5 problems. Maybe we'll have 2 problem challenges again, and that will add up to 2. It depends upon how well we're able to combine some topics. As a reminder, I will be taking questions on these particular problems during an ORT session this week. These problems will not be graded, but it is in your best interest to do these problems to prepare you for both the homework and the first quest. All of the answers to these problems should be available in the back of the book, which again should make things go fairly smoothly. And as always, if you come up with questions about this material that you'd like to pose before our next class, remember you can either email them to me at miaresj@d2l.lcc.edu, or you can post them to the discussion board under the general questions and items to share forum. Thanks for watching, and we will see you all soon.